So, hey guys, welcome to another day of DSA learning, and let's begin. Yeah, so it's day number. You can check it into the thumbnail. And right now we are learning graph. So, if you wanted to follow along, maybe you can practice along with me. Just let me know in the comment section. And right now we are solving the graph problems, and I'm following the driver's seat. So let me transition, and here we go. Jump to take you forward, quick time player. Oh shit, just give me a second. Seems like I'm logged out. Okay, login. Shit. No, you don't need to do this. Yeah, this is the account. So logged in. What? Already logged in, bro. Why are you saying? Oh, I need to finish these things as well. To be deprecated against computer network. Why? Then what you'll add? But I want to learn computer network maybe because my okay seems like they have created one more lecture where Striver is teaching computer network. Because people, I saw some people were complaining like the content quality is not good, so it might be okay. So these things, there are a lot of things that needs concept revision. I will learn them, but not now. First, let me just go to the not plus dashboard. Let's go directly to the. I'm following the simple dash, simple generic penric. What is it? Topo short. So Alien dictionary is pending still. I'll do it later. We started shortest path algorithm. Shortest path in DAZ. It was little complex to me. Shortest path in undirected graph. It was simple, but here the concept was used topological sorting to get the sorted order of the nodes and then apply the what we were applying. Said bro, fuck. Maybe I need to restart. It's irritating. Irritating. No. It will start from here. I just turned off. Kept the fan speed low because yesterday I noticed it is creating a lot of noise, and because of that, if someone is gonna watch, couldn't hear me properly when I'm silent until I'm speaking. It's okay, but it's Castra algorithm. It's pretty famous algorithm. We are going to follow it, but I'm just recalling what I did yesterday. This was a simple problem where I was keeping the length and then I was adding it, and I performed a level order traversion. That was simple. It's a simple approach. But in case of DAZ, we need to explore all the paths. So not we need to explore all the paths, but you are going in a BFS way only. You can say. So first we did simply we performed topological sorting, and then just you are looking for its neighbor. You are popping out one by one node from the stack, and then you are resolving the values. Still, it's a pretty unintuitive. Unintuitive. It's a incorrect word, right? Unintuitive. Unintuitive. Do means something that is hard to understand and used by. Is it correct? Yes, unintuitive is a real word. Fuck. I don't know. This Castor algorithm. Okay, so solve. I will go to the solve and I'll follow the tutorial part here. So this is an algorithm. So definitely I will watch video time complexity and in-depth theory. Okay, so definitely it need a lot of time to learn it properly. So I'm just sharing with if someone wants here. I don't know if I will say no, it won't work. So let's start. Disgastra.
So we will be starting off with Dijkstra's algorithm in this video.
Using periodic queue.
So we will be starting off with Dijkstra's algorithm in this video, and this is one of the most important algorithms.
What?
Dijkstra's algorithm in this video, and this is one of the. We will be starting off with Dijkstra's algorithm in this video.
Disgastras. Dijkstra. I pronounce Dijkstra. Algorithm pronunciation. Dijkstra algorithm. Okay, forget about this. Let's say this. Dijkstra. Let me.
Dijkstra.
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 Dijkstra. Dijkstra. Okay, so J is silent here. Dijkstra. Dijkstra. How he pronounced?
Dijkstra's algorithm in this video, and this is so we will be starting off with Dijkstra's algorithm in this video, and this is one of the most important algorithms if you're solving problems related to shortest path. Okay, now what does this algorithm state? The algorithm is very simple and straightforward. It states that you'll be given a source node. Assume over here I'm saying that the source node is 0. What does the source node means? The starting point. This is where you're going to start. So I'll be like, okay, the source node is 0. In order to reach 0, what will be the distance that you'll take? You'll be like
0.
0. From 0 to 0, 0, right? But if I ask you, from 0 to 1, what will be the distance that you'll take? Now, what is distance? From 0 to 1, you can go via various paths. You can travel directly. And if you travel directly, this is the edge weight that lies on that path. And that is what the weight of the path is. So I can say, if I travel directly from 0 to 1, the weight of the path will be 4. There can be multiple paths. One of the paths can be this, which travels via 2. And if it travels via 2, there's a 4 and there's a 2 line. And that will give a total path weight of 6. Right? There can be other paths as well. When you decide that you're going to take an entire journey of the graph and then come, there'll be more. 4 plus 3 plus 2 plus 3 plus 1 plus 2. But what I'm concerned about is to find the shortest one. So can I say the shortest one is 4? Right? And if this would have been something like 1, can I say the shortest would have been then this path, which is 1 plus 2, 3. Right? So the task is very simple. Give it a source node. Give it a source node. From that source node to every node, yes, to every node, you have to find the distance. So till 2, you have to find the distance. That will be something like again 4. Till 3, you have to find the distance. So what you need to do is you need to make sure from 0 to all the nodes, from 0 to 0, 1, 2, 3, 4, 5, 4, I should know what distance will I take as the shortest one, because I need the shortest one. That is what you need to tell me. And that is what the Dijkstra's algorithm will help us to find. Now, Dijkstra's algorithm can be implemented by 2 methods. One of them is actually 3. Like you can go across to 3, but one is priority queue. The other one is the set. So you can use the data structure priority queue. You can use the data structure set as well. You can also use the queue, which is the third one. But this will take more time. Priority queue also takes a bit of time. The set is the fastest. So in this video, I'll be telling you the priority queue approach. Then in the next video, I'll be teaching you the set method. And I'll also be covering the intuition. I'll also be covering why priority queue, why not queue. I'll be covering all the questions that you will have in your mind when you go through this particular algorithm. So you don't need to worry. Just to make sure each of the videos, watch till then. I've seen a lot of people skipping a lot of portions, but I do say a lot in between as well. So do not skip. Make sure whatever videos I make on Dijkstra's algorithm, watch them one by one. It can be 3 or 4, but make sure watch each and every video to get the concept clear. Because once the concept is clear, then we will move to solving problems. Yes, we'll be solving a bunch of problems. And at the end of the day, you can solve any problem of Dijkstra's algorithm that comes in your interviews. We will be implementing the Dijkstra's algorithm using the priority queue. So the graph can be represented in an adjacency list. And this time we'll be storing pairs. Okay, so something like if 0's adjacents are 1 and 2. So I store something like 1, 4, which is basically the node and the weight. The node and the weight of the edge. Something like 2, 4. The node and the weight. Node and weight will be stored. So this is how you can store the adjacency list. So if you're standing at 4 and if someone does ask you what are the adjacent nodes of 4, you'll be like 2 and 5. What is the weight till 2? 1. What is the weight till 5? 3. This is how you can figure out from the adjacency list. So in order to implement this particular algorithm, there is an initial configuration that we will start off with. We will always have a mean heap data structure. And the mean heap data structure will always store a pair, a distance and a node. Remember this. What is a minimum heap data structure? So if you're storing anything in terms of distance and node, the shorter distance, I repeat, the shorter distance will be at the top, right? And if there are equal shorter distance, the earlier node or the shorter node will be at the top. You'll understand as we move. We will always have a distance array, which will keep track of how much distance are we taking in a path, okay? And we will have the source node. And source node can be 0, can be 1, can be 2, can be anything. So as of now, the source node is 0. So the first step of the algorithm is very, very simple. What we do is, we say rather that the source node is 0. So from 0 to 0, we are definitely sure that the distance will be 0. So we go and put a distance 0 in the distance array, and we say 0 distance, 0 node, and we put that into the minimum priority queue. That's the initial step 1. Now we start the iteration in the priority queue, and it's similar to BFS. We start the iteration, we take the topmost element in the priority queue. As of now, there's only one element, so we just take it out because that's the topmost element. So we are saying we're taking a distance of 0 in order to reach node 0. We're taking that much of distance in order to reach node 0. So 0 says, hey, where can I go? 0 is like, I can go to 2 and I can go to 1. There are two ways in which you can proceed from 0, right? And how will you figure this 1 and 2? If you remember, adjacency list will tell you about that, right? So just figure the 1 and 2 from there. So I can actually move to something like node 1, and how much distance will I take? If this is taking plus 4, this is going to take 4. Why? Because previously I did 0, I'll take another 4, which will make me a distance of 4. Remember, previously you will be marking all these distance as infinite, a very big integer, which will mean that you never reached those nodes. So in order to reach node 1, you're taking a distance of 4. Can I say it's better than previous? It is. So go and just replace it with a node with a distance 4, take the 4 and the node 1, put it into the priority queue. So I repeat, every time you get a distance, which is better than the previous distance, that means you discovered a new path and you take that distance and put it into the priority queue always, okay? Or the next thing, you can always go to the node 2, which is the next adjacent. If you carefully see, node 2 is the new adjacent, which you can go at a 4, like it's another 4, so the new distance taken will be another 4. And 2 previously was infinite, 4. So 4 comma 2 is what I'll put into the priority queue. First iteration done. Similar to BFS. Next, who will be at the top of the minimum heap? Can I see? 4 comma 1 will be at the top of the minimum heap. 4 is equal in both of them, but 1 is smaller. Minimum heap. So 4 comma 1, yes. So I'm saying I'm taking a distance of 1 in order to reach the node, distance of 4 in order to reach the node 1. Very obvious. From 1, where can you go? Again, you look at the adjacency list. It will say you can go to 0 and you can go to 2. Correct? So go to 0. So you can go to 0 and that will take a distance of 4, which will make it a total distance of 8. Will you consider this? No. Why? 0 is already reachable at 0 distance. Not to be considered. Where can you go? You can also go to the node 2 by taking a distance of
I got confused.
Can I say it's storing anything in terms of distance and node? The shorter distance, I repeat,
Distance
the
node,
shorter
okay.
distance will be at the top, right? And if there are equal shorter distance, the earlier node or the shorter node will be at the top. You'll understand as we move. We will always have a distance array, which will keep track of how much distance are we taking in a path, okay? And we will have the source node. And source node can be 0, can be 1, can be 2, can be anything. So as of now, the source node is 0. So the first step of the algorithm is very, very simple. What we do is, we say rather that the source node is 0. So from 0 to 0, we are definitely sure that the distance will be 0. So we go and put a distance 0 in the distance array, and we say 0 distance, 0 node, and we put that into the minimum priority queue. That's the initial step 1. Now we start the iteration in the priority queue, and it's similar to BFS. We start the iteration, we take the topmost element in the priority queue. As of now, there's only one element, so we just take it out because that's will be the topmost element. So we are saying we're taking a distance of 0 in order to reach node 0. We're taking that much of distance in order to reach node 0. So 0 says, hey, where can I go? 0 is like, I can go to 2 and I can go to 1. There are two ways in which you can proceed from 0, right? And how will you figure this 1 and 2? If you remember, adjacency list will tell you about that, right? So just figure the 1 and 2 from there. So I can actually move to something like node 1, and how much distance will I take? If this is taking plus 4, this is going to take 4. Why? Because previously I did 0, I'll take another 4, which will make me a distance of 4. Remember, previously you will be marking all these distance as infinite, a very big integer, which will mean that you never reached those nodes. So in order to reach node 1, we're taking a distance of 4. Can I say it's better than previous? It is. So go and just replace it with a node with a distance 4, take the 4 and the node 1, put it into the priority queue. So I repeat, every time you get a distance, which is better than the previous distance, that means you discovered a new path and you take that distance and put it into the priority queue always, okay? Or the next thing, you can always go to the node 2, which is the next adjacent. If you carefully see, node 2 is the new adjacent, which you can go at a 4, like it's another 4, so the new distance taken will be another 4. And 2 previously was infinite, 4. So 4 comma 2 is what I'll put into the priority queue. First iteration done. Similar to BFS. Next, who will be at the top of the minimum heap? Can I see? 4 comma 1 will be at the top of the minimum heap. 4 is equal in both of them, but 1 is smaller. Minimum heap. So 4 comma 1, yes. So I'm saying I'm taking a distance of 1 in order to reach the node, distance of 4 in order to reach the node 1. Very obvious. From 1, where can you go? Again, you look at the adjacency list. It will say you can go to 0 and you can go to 2. Correct? So go to 0. So you can go to 0 and that will take a distance of 4, which will make it a total distance of 8. Will you consider this? No. Why? Which will make it a total distance of 8. Will you consider this? No. Why? 0 is already reachable at 0 distance. Not to be considered. Where can you go? You can also go to the node 2 by taking a distance of 2. Why? From 1, if you go to 2, you take a distance of 2. Easily figured by the adjacency list. So plus 2 plus 4 equals a total distance of 6. Is it considerable? No. Why? Already reachable at 4. So no one was taken into consideration. Done. Let's go to the next one. Only one guy out. Takes a distance of 4. I don't know, 2. Where can node 2 go? Again, look, stand at the, or look at the adjacency list, and you will see that 2 can go to 0, 2 can go to 3, 2 can go to 4, 2 can go to 5, 2 can go to 1. It can go to everyone. So I'll try to go at first to node 0, which is going to take me 4. To make me a total distance of 8, not to be considered. I'll try to go to node 1, which will take me plus 2. They make the total distance 6, not to be considered because we still have better alternatives. Next, I'll try to go to node 3, which will take me plus 3, which will make me the new distance 7. Understood? Previously did 4, from 2 to 3, 3, 4 plus 3, 7. 3 is infinite, someone better. 7 better. So 7 comma 3, we got someone better. Next, I'll also try to go to node 4 by taking a distance of 1, which will make it a distance of 5. Again to be considered, 5 comma 4. Next, I'll try to go to node 5 by taking a distance of plus 6, which will make me a total distance of 8. Again, 4, 6, this 6. Distance 10, better than infinity, to be considered. So I'll take 10 comma 5, put it into the priority queue. We got 3 guys that went into the priority queue. We got 2 guys that got discarded. Let's just omit this off. What's the next step? Who is the topmost element in the priority queue? Or minimum heap. Get it out. There's 5, there's 7, there's 10. The 5 comma 4 will be at the top. So 5 of a node 4. 5 at a node 4. Where can node 4 go? It can go to node 2, and it can also go to node 5. You can observe from 4 you can go to 2, you can go to 5. Easily figured out by the adjacency list. So from 4 to 2, distance of 1, 6, not to be considered. From 4 to 5, 3, distance of 8. Will you consider this? Yes, because you got a better one. So 8 comma 5 will be considered. 8 comma 5 will be considered. Okay, done. Perfect. What's the next thing? The next thing is who will be the next guy. So we have 7, we have 10, we have 8. 7 comma 3 will be the next guy. So distance of 7, node 3. So where can 3 go? Let's stand at 3 and see. 3 can go to 2, I think 3 can go to 5, 2 pieces. 2 and 5. So it will try to go to node 2, take a distance of 3, make a total distance of 10, which will not to be considered. It can go to 5, by taking a distance of 2, it will make a total distance of 9, not to be considered because we have 8. We have 8. Got it? So no new results. Omit this. Next, we'll take the next element out, which is, so 8 comma 5 is done by the way. Sorry, 7 comma 3 is done by the way. Next, you'll take the next out, which is 8 comma 5. So distance of 8 to node 5. Where can 5 go? Where can 5 go? 5 can go to 2, 5 can go to 3, 5 can go to 4. So we'll try to go to 2 again with 6, which will make a total distance of 14, not to be considered. We will try to go to 3 with a distance of 2, which will make a distance of 10, not to be considered. We'll try to go to 4. Yes, we'll try to go to 4 with how much distance? We'll try to go with 3, which will make it 11. 4 is better, not to be considered. Similarly, you will again take out 10 comma 5 this time. And again, you'll try out 3, 4, 2, and none of them will be considered. So apparently better. It's apparently better. And once you're done, you will see this distance array stores the minimum. If you see till 5, it is saying 8, which is very much sensible. Why? Because if you carefully observe, from 0, you can go to 2, which will take you a distance of 4. Then you can go to 1, then you can go here. So in this way, you can actually take 4 plus 5 plus 3, which is 8. All the other parts, even if you're trying to take this, it's going to cost you 9. So all the other parts will cost you more. So you got your minimum distance stored in your distance array. If you return this distance array, this is what your particular answer will be. So guys, I hope you've understood the algorithmic explanation of Dijkstra's algorithm.
Still, I need to rewatch. Better. What I'll do, instead of rewatching, I will do it by self. See, they kept like if you are sharing your screen, yes, it will turn into white screen or black. So let's do it. Okay, we have a graph 0, 1, 2, and then 3, 5, from here 6. Okay, 4, 4, 1, not 1, 2, 1, 3, 6, 3, 2. Okay, so here this is a graph that is given, and we need to apply this Dijkstra. I'll go using min heap. Min heap has a property like whenever you are adding something, adding an item, it will keep at the top as the minimum element. So it built like a tree, where at the top always you are going, whenever you will insert, suppose the tree there was 1, 2 and 5, and now you added one more item that is 0, then at the top 0 will be at the top. Have you got the property? So simply what it does, I remember something I haven't covered tree. Basically what we were doing, we are inserting it somewhere at the bottom, then we uh, and then we what we do, simply we reshuffle, or we basically change the state of it. Okay, let's forget about it for the timing. Let's focus on it, because once we'll get the step 1, so we'll keep distance array. So how many nodes we have? 5. 0, 1, 2, 3, 4, 5. For each node distance. So at the starting what we'll do, I'll keep infinity, and for 0 I will keep 0, because this is the one node, this is our queue. So at starting what we will do, we are starting from here. At the starting what we'll do, so we need to keep minimum distance at the top, and node this uh, in this way we will store into the queue min heap. Okay, so let's do one thing. Simply what we'll do, we'll start from 0. So for 0, what is the distance? It will be 0 comma uh, 0. For 0, distance is 0 for 0. Okay, then we'll pop it out, and we'll compare again whether the distance of this is 0, and or we don't need to do this that. So let's add one more. Now we'll explore its neighbors. What are its neighbors? You can check into adjacency list. So its neighbor are 1 and 2. So what we'll do, let's say we are choosing 1 or maybe 2. It's up to us, right? So suppose I'm choosing 2. So for 2 what will be? Uh, it will be something like 2. You choose 2. So for 2, the distance will be distance of the previous node from which you are calling. So 0 plus 4. So for it will be 4 comma 0 plus 4, 4 comma node is 2. Okay, so you will say, okay, 4 is better than whatever the length for 2 is. So you will change you will change it to 4, and this is not done. Yeah, now you will look for the 1. For 1, what is the distance? So you will say for 1 it is uh, 4. So 4 comma 1. So these are the two things. Now if two nodes have same distance, will it restructure them based on how exactly we are going to do, based on this, or we can adjust? I need to know. Logically it should do something like 1 should be at the top. Here it is already at the top, but because the distance is same for both, so I don't think that there will be any issue from 1 and 4 and 2. Let's say, okay, now there will be queue like item, so it's a priority queue. So min heap, so according to that Imagine, let's do what will be wrong if it is the case. We are not shuffling, we are just shuffling based on distance. So here this, so we'll go to 4 2. 4 2 will do what it will do. So second node, and the distance is 4. So second node will try to uh, go to its neighbor. So for second node, what are its neighbor? 3 6 4 and 1. 0 1 3 5 4. So let's start from any node. We can start from any node. So if we'll say for 1, what exactly the distance is from here. So you will say for it, right now distance is 4, and now you are moving to 1, so it will be 6. So for 1 it will be 6, and here right now we don't have anything, so we can change it to 6. Okay, so based on this node, this one we are processing right now. Okay, and now you will say, okay, what if I'll move to 0? For 0 you will say, okay, 0, and if I'll add more, then it will be 4 and plus 4, so 8. Definitely you won't do that. Now you will go to 3. For 3, 4 plus 3 7. Right now we have 4 distance at node 2, and when you are taking you are moving to 3, it will become 4 plus 3 7. So for 3, right now we have infinity, so better than infinity. Now you will say for 5. So for 5, 4 and 6, for 5, 4 and 6, 10. So it will be 10. Now you will move to 4. For 4, it will become 4 and 1 5. Oh, sorry. I forgot to do the one thing. Whenever we are making a change, or whenever we are using something, or whenever we are basically updating, or we are getting minimum, so we need to add it into the list, right? For example, for 1, uh, right now we got 6 earlier. Okay, for 1 it will be 6. 1 is not processed yet, so we'll say uh, 1 comma 6 comma 1. Okay, one thing, and another 3 comma, I mean, for 3 it's 7 comma 3, and one more, it will be 2 comma 5. Okay, so for 5 it will be 4 and 6 10. So 10 comma 5. Okay, for this 4 it will be 4 1 5. So 5 comma 4. So these are the nodes that we have right now. Okay, based on this processing, so this one done, this one done. Now we'll move to uh, not we will move to, basically we need to process the minimum distance from this. So 4 will come first. So let's say 4. So what is 4 1? 4 1 will be something 4 1 first node, and you are having distance of 4. So from here you wanted to move to its neighbor. So you are at this node. Now you wanted to so its neighbor are 0 and 2. So if you have already 4 distance from 1, and now you want to 0, so it will become 8. That won't be here, or it's not going to replace it. So that means you won't do anything here. And now if we talk about 6 2, so for 2 right now we have 4, and here we will be having 4 plus 6, so you won't do anything, so just pop out. Now we will move to another min item, and that will be this one. All right, so 5 and 4, so node is 4 and length is 5. So node is 4, node is 5, oh sorry, node is 4 and length is 5. 4 1 5. So 5. Now you will look into, okay, 4 1 5. So you already processed. Now you will just check its neighbor. So for 5, for 4, its neighbors are 5 and 2. So if you are going back to 2, then what will be the distance? So you are going back to 2, so it will be like you have already have 5, you have 5 distance, and now you want to move to 2. So 5 1 6. So you will check for 2, what is it? So 4. So 4 is already better, so you won't do anything. Now let's look about this neighbor. So for 5, it will become like a 4 1 5. So 5 we have 5 3 8. So for 5 right now we have 10, so it will become better, it's better, so 8. And now you will append it into the min heap. So min heap, it will be like 8 and 5. Okay, now we'll see another min item from it. So it is 1 and 6, 6 and 1. So if we are going to process this item, so right now we have 6 1. So if we are going to process 6 1, then okay, node is 1 and distance is 6. Okay, so from node 1 you will check again. So from 1 you will say, okay, for 1 what is distance? Right now 6. And now you have two options. Either you can go to, so you can go to this node. Hmm. Huh. Sorry. So from 6 1 1, so 6, and now you wanted to explore its item. So 1 to 0, 1 to 2. So you have two options. So if you are going to 6 plus 4 10, that means it's already not efficient. Then you will move to 2, and for the t it will be like 6 plus 2 8, and for 2 it's already 4, so that is not also not good. For 7, now you will see these are the three things. So 7 8 10, definitely you will go with 7. For 3, where is 3? It's a 7. So from 3 you can move to 2, 5, and you can move to 2. Okay, you can move to 5, you can move to 2. Okay, so from 3 you can move to 5 2. And for if you are going to move to 5, then what will be the distance? Right now for 3 it's 7, so 4 3 7 plus 2 9. So for 5 it will be 9, and right now we have 8, so it's already better, you won't do anything. From 3 you will move to 2. So if you are moving to 2, 7 plus 3 10. Definitely it's not it's for 2 it's already 4, so it's not going to help. So this is also done. 10 5, I got it, one issue is there. So 10 comma 5, for 10 and 5, so node 5 and distance is 10. So for 10 you can say 6 plus 4 10, and so 5 it is 10. So let's see if we'll go with 5 and 10. So you will say, okay, for 5 what are the different options available? For 5 its neighbor are 3 and 4. So if you are applying 3, you are going to reaching to 3. So 3 will be 10 plus 2 12. So 12 for 3. For 3 it's already 7, so better than this. For 4 you are again going to do what? 10. I'm so bad at it, fuck. We will solve this one first. 8 and 5. So 8 and 5. So from 5 you have 8 distance. Let's see from where we are getting. 4 3 7 2 9. 4 1 5 3 8. This one, this path we follow. So for 5 its neighbor are what? Its neighbor are 3 and 4. So if you are going from 5 to 3, then it will be 8 to 10. For 3 it's already 7, not it's a bit better than the existing calculation. And now you will say, okay, 5 to 4, if you are going, then it will be like 4, already 8 plus 4, 3 11. So for 4 you are getting 5, so this is also done. 10 5 definitely it's also done, it won't help. But you know one thing is wrong here, and that is this one, this part. For this one we are getting 6 from this path you calculated, and that's the wrong thing. And the reason is simple because here I choose these. There were two things, so 4142, and I chose 42. Ah, I think the issue is I'm not checking the existing distance that we have. Where is it? I will rewatch the video first.
So there is an initial configuration that we will start off with. We will always have a mean heap data structure, and the mean heap data structure will always store a pair, a distance, and a node. Remember this. What is a minimum heap data structure? So if you're storing anything in terms of distance and node, the shorter distance, I repeat, the shorter distance will be at the top, right? And if there are equal shorter distance, the earlier node or the shorter node will be at the top. You'll understand
Okay.
as we move. We will always have a distance array, which will keep.
So there are two things. First, compare distance shorter. Then, if distance are equal, then shorter node. If both are tying, then first compare this. If tie, then this.
Track of how much distance are we taking to carry one purpose. We see. Definitely sure that the distance will be 0. So we go and put a distance 0 in the distance array, and we say 0 distance, 0 node, and we put that into the minimum priority queue. That's the initial step 1. Now we start the iteration in the priority queue, and it's similar to VX. We start the iteration, we take the topmost element in the priority queue. As of now, there's only one element, so we just take it out because that will be the topmost element. So we are saying we're taking a distance of 0 in order to reach node 0. We're taking that much of distance in order to reach node 0. So 0 says, hey, where can I go? 0 is like, I can go to 2 and I can go to 1. There are two ways in which you can proceed from 0, right? And how will you figure this 1 and 2? If you remember, adjacency list will tell you about that, right? So just figure the 1 and 2 from there. So I can actually move to something like node 1, and how much distance will I take? If this is taking plus 4, this is going to take 4. Why? Because previously I did 0, I'll take another 4, which will make me a distance of 4. Remember, previously you will be marking all these distance as infinite, a very big integer, which will mean that you never reached those nodes. So in order to reach node 1, you're taking a distance of 4. Can I say it's better than previous? It is. So go and just repeat
This. So let's solve it. I got done tuition. Now just let me think about the input. So we have given ages. What is the value of s? V vertices numbered from 0 to v minus 2 array, which represents the ages. And what is s? S is the length of. Oh, sorry, source. I'm so sorry. Given a node source, find the shortest distance from all the vertex uh, of all the vertex from the source. Return list of integers denoting shortest distance between each node and source vertex itself. If a vertex is not reachable from the source, then its distance will be 10 to the power 9. 10 to the power 9. Okay. And what is the distance? I just wanted to see. Can the result be greater than this 10 to the power 9? I'm assuming no. Or let's do one thing. Just assuming, okay, so all the distances will be lesser than this. Okay, so let's build the adjacency list first. Distance list. Create the distance. So distance will be something like here. I will keep everything max. Let's say 10 to the power. Okay. Max will be 10 to the power 9. So for Maxwell, for underscore in range, and v number of vertices for each vertices starting from 0 to v minus 1. So okay, it's okay, distance is okay. Now distance we created, build adjacency. So for uh, okay, for I in a range, you can say, okay, let's do one thing first. DSA is nothing but list of underscore in range v. So I'm just creating an adjacent blank adjacency list of lists, list of lists, tongue twisting, lists, collection of list, better, list of list, no, list of lists for I in range. And here we are going to len of h's. Okay, now what I'll do, oh, I don't need it, this, bro, why are you doing this? I get confused. For edge, in edges, so each edge, so it's undirected, so differently u and v and w, three things will be there. So what you are going to do, so weight edge, and you we are unpacking the value and adjacency of u. For u node, uh, for you will append it v, and vice versa. Here you will say for v we are going to append u. Okay, vu. And oh, so bad, here don't forget to add v and weight, u and weight, so it will be tuple. So this is done. Next step, first we created distance, the second we created this, then third this, and fourth, what was it? hmm I forget, I mean, oh god, it's a discastra. So discastra, okay, we have a queue. Yeah, priority queue, I don't know how to create it in Python. How to create priority queue in Python, bro? I know. You can create priority queue in Python using two primary built-in tools: heap queue, recommended for speed, and standard algorithm queue.priority. I will do one thing. I will see the tutorial, and there they have used it. They will be using it, or impute heap queue. I'm just wondering if suppose I'm appearing for an assessment, and there they haven't provided, there isn't option to import it. I will cry. Then I don't. Maybe I need to then implement it first, but it will eat a lot of time. Okay, I don't need to watch the tutorial, so definitely I will skip it. I mean just this escape option is coming. Bro, fuck. What the heck? Stop it, Google. Stupid. Sorry. How to create priority queue, and then it will tell me heap queue dot push insert item priority queue. What kind of queue it is? PQ empty PQ dot heap push. Okay, PQ. Okay, you pushed two things. Top priority task 1 and 2 medium priority task. Well, acha. From queue import priority queue. Thread safe, I don't know. fastest and standard order of login. It provides time complexity for insertion and extraction. Login, perfect. Add item is heap queue is min or max. Looks like it's min. What if I am using tuple values? Tuple values value. Use tuple value in menu apply. First elements are equal, it move to index 1, then index 2, and so on. Perfect. So it's okay for us. So just I need to remember heap push and heap queue, heap pop, heap push, heap pop, heap push, heap pop. Okay. So pro distance of 0 will be 0. Set distance of s will be 0. S for start. And second thing, so we need to append. So first need to create. So HQ I'll use heap queue and it will be heap queue. No. What was it? Structure. Okay. Heap queue. You are using simple list and then you are just every time adding it. Weird. Why don't they created one object and we need to be it would be very easy for us. So HQ, let's say, and then okay. What I'll do simply, this is our heap queue and I'll push first item. So heap queue dot heap push and I will push two things. First thing is just pass the list that you are creating as a heap queue. Second thing, pass the item that you wanted to push. So I want to push the value 0 is the distance and the value and node is s. Now this is done. While HQ is not empty, I will be having two things. D node distance, I will use just struct node and then I will say okay, so I got two things. Now we just need to pop. So heap queue dot pop heap pop. I think then we again need to pass the value pq. Yeah, very weird way to use it. Heap queue, heap pop. So we got the item. Now what I need to do, so whenever you are getting an item from the queue, you are going to explore its neighbors. So for neighbor in adjacency of NBRs, sorry, NBR node, you are getting, and now what you will do, simply you are going to push them into the queue. For each node you are going to push only if if hmm. So first let's calculate for this neighbor what will be the distance, new distance. So new distance will be, I'm using descriptive variable name, and new distance will be something where you will be having distance that you are getting for this node. So dist plus okay, here two things we are getting, weight. So plus weight. Wow, pro. Now if new distance, is less than the distance of this. So I'll say distance was what was distance only, distance of neighbor. So if it is lesser than neighbor, then that means you can append it. So this is the right way. So I will say okay, heap q heap q dot heap q dot heap push and hq and then value. So it will be something like a neighbor, no, new distance and node neighbor. So these are the two things that you are passing to it, and you are going to perform this again and again, and at the end you will get the result. Am I missing anything? Return distance. I just want to see it because completely it's new, and I'm also confused with heap queue how to use it properly. Discustra, I created Maxwell distance, and here I kept everything. So I mean I'm starting from the source node. So okay, it's okay. Here I just did one thing. I just building adjacency list with the node and weight. Discastra. So here created one empty list and distance of this source node 0, and I'm just what I did simply I'm pushing the first item or source node with the just distance 0, so distance and 0. Then I'm just iterating while the queue is not empty. So this I'm getting distance plus node value from the this queue, and then I'm iterating through all the neighbors of this node and then getting neighbor and weight. New distance will be distance plus weight, checking if new distance is lesser than the distance that we have right now in the neighbor in this node for this node. So if then you will push hq new distance neighbor, and at the end you are going to get the distances of all the items or all the nodes. Where I defined pq. What is this pq? Hq. I think I just made something. Okay, let me just check one more time what's wrong with it. Credit distance, this I just source is 0. Print adjacency. I think it's okay. Let's see. 0 to 1. There will be only 1. 1 to 0. For 0 it's 1. For 1 it's 0. And the weight is 9. Okay, that is okay. So adjacency list is okay. I believe the problem is execution, this one. HQ distance is equals to 0. 0 is distance will be 0. You push the item. Now you started checking one by one. Distance node heap q heap pop HQ for each neighbor node and wait. New distance is nothing but distance of the node, and from that node you are going to move to these nodes. I feel it's okay. Sorry. Where is I will see the editorial, I think. Oh shit. One thing I forgot. So distance of that neighbor will be new distance. So this one done. Now I just need to watch another tutorial using sit first. By the way, this is my question as well. Why are we using uh, priority queue? Why don't we use queue? What will be wrong if we'll use queue? Come on, man. What's wrong with you? Let's think about it. I mean, just yeah. Then only we get the reason behind it. If I'll use simple queue, then what it will do? Simply we are moving from 0 to 1 and 2. Correct. We are moving to 0 from, so first we'll add, let me just draw, I mean let's deep dive into it. So this is our new graph and new distance. Sorry for the 2, 3, 4, 5. So these are the distance. By the way, not this one I color use. So 0, infinity, 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 infinity at starting. So I will use 0. Let's say if I will use this 0 and distance is 0 and for 0, then it is done. So what you'll do, you will pop it out and you will say its distance is already 0, you kept it. Now you will move to its neighbor 1 and 2. So simply maybe we are starting adjacency, so it will, you will add 1 and 2, sorry, you will add 1. What is the distance for 1? It's 4. So for 1 distance is 4. So from 0 to 4, so 0 this distance plus this 4. So here you will say 4, and what is the value? for 1, and for 2 it will be also 4, so 4 comma 2. Okay, now it's okay, correct. Simply what I'll do now, I will move to from, I will start. Okay, now I will pull out one item. So we just did, imagine first I did, okay, no matter. So I'll use 1 4. Okay, now for 1 and 4, right now you will see, okay, what is the distance. I made some mistake, right? For these two values it will be 4, and for 2 it will be for 2 it will be 4. Now we are going to, from 4 1 to, sorry, from 1 4, node 1, and your distance is 4. You can move to 2, you can move to 0. So if you will move to 0, then distance will be 4 plus 4 8. So that is less higher than the existing value, so you won't do it, you won't do anything. Now from you are, if you are moving to 2, then 4 plus 2 6. So 6, can you say 6 is better than the value that is existing value 2? No, so you won't do anything. Now you will move to 4 2. So from 2 you can move to 1 0 3, all the nodes you can access. So 4 2, you will mark it done. So 4, if you are moving to 1, then it will be 4 to 6. So for 1 it's 4 already there, it's better. So now you will move to 3. So 4 plus 3 is 7. So you will say 7, it's not there, it's better than infinity, right? 7 and 3, first thing. Another 4 plus 6 10. So for 5 you will say, okay, 4 and 6 10. And another one 4, you will say 4 1 5. 5 is better than infinity, so 5 comma, you will say 4. For 4 it's 5, for 5 it's 10, for 3 it's 7. So it's done. For 0 it won't do. Now you will move to, now as per this logic what you can happen, it depends on the adjacency list how you added, and anything can randomly come. So let's say 7 3 is coming now. So from 7 3 what you will do, from I think I made one blunder. For 3 it will be 7, here I forgot to update. For 5 it will be 10, and for 4 it will be 5. Now we are exploring 3 7 3 3. So 3 it's right now 7. So you will say, okay, from 3 where you can reach, you can reach to 5, you can reach to 2. So if you are reaching to 2, then it will be 4, what is right now 7, 7 plus 3 10, 10 for 2. 4 is, it's better already, the value, better value is here, so you won't do anything. For 5 if you'll say, then you'll say 4 3 7, 7 plus 2 9. So for 5 you will say, okay, 9 is better than this value, so why don't I update it 9. Now you will say, okay, I'm updating the value, then why don't I add this node? So you will say 9 and 5, you will add it into it, you will add it into the queue. 9 and 5 is done. No, not done, but newly added node. And okay, you are done for 7 3. You will move to 5 and 10. 5 and 10, you will say 5. For 5 the value, okay, for 5 the value is 10 right now. So what if I'm using this approach, then 10. Now from 5 I can move to 2 and 4 and 3. So first let's start with 3. For 3 it will be, so you are moving from 5 to 3. So 5 distance required to reach 5 is 10. 10 plus 2 12. 12. 12 for 3. No, it's not good, because 7 is better than this, so you won't do anything. Then you will move to 4, let's say 2. So you will be having 5 and 10. You are processing this one. So 10 plus 6, 16. 16 for 2. It will say, are you stupid? Or what? 4 is better than 4. So you won't do anything. Now you will say, okay, for 3, for 4, let me check. So 10 plus 3, 13, 4, 5. So it's already better. Now you will move to 4 and its value is 5. So 4, its value is 5. So 415. So okay, now you can say 4 2, you can move 2 and 5. So 2, it will become like a 5 plus 1 6, and for 2 it's already 4 better, so you won't do anything. This one I am processing right now. And for 5, you can say okay, 3 4 1 5 5 plus 3 8. For 5 you will say okay, 8 is better than 9, so why don't I change it to 8? So you will change it to 8, looks better, so you will do that. Okay, this is done. Now 9 and 5. 9 and 5. Oh, sorry, 5 and 9. So 4 6 10, 4 3 7 2 9, and 4 1 5 3 8. So let me see. For 5, the value is 9. 9, and you are moving from 5 to basically 4 and 3. So if 9 plus 3, 12 for 4. No, it's not better, so you'll skip. Then same for 5 to 3, and this one is also not good, so you skip. Done. But here I'm getting the same result. Am I missing anything? Thanks, bro. Okay. Why are we using this? Okay. Is there any AI option or what? Let's do one thing. I will here were some simple questions, right? Why don't I utilize them? Frequently asked? No, it's here only. Why does this not work with negative weights? Negative weights. Oh shit! I have to think about it. If I will use negative weights first thing, then what will be wrong? Suppose I'm moving to somewhere. Since it processes each node once, process node once. Really? Okay, one thing I'll do. I need to dissect it. This is our source node. I think I learned the algorithm but not intuition. So whenever you are adding a node, what exactly you are doing? So for example, you added 0 into the queue, and now you are going to visit its neighbors 2 and 1. Then what you are doing? You are adding them into queue. priority queue, and then you are checking the distance for them from the source node, and then accordingly you edit them. Then what happens? Suppose you are getting minimum here and here, so both having same, but imagine these are the different nodes. So exactly what you did, simply you are inserting a node into the queue, and then minimum you are taking out. If you won't take the minimum, you are taking out minimum one, right, out of the nodes that are there. A reasoning behind it. Behind it. I think 0 to moving to, for example, shall I take one more example of what? 0 to 2, 0 to priority queue. If I won't take priority, then it will be normal queue. So what will happen? Suppose you are processing an item. Let's think about it. What will happen if I will use this one instead of this one, priority queue? Then simply, for example, you got, first you will start add starting node. Then you will add some of its neighbors. So there will be, let's say there are neighbors A, B, and C. C is minimum. So you are going to process that node first. Hmm. And when C, you will process C, you are going to look for its neighbors and you are going to push them into the queue. And now you will choose the minimum out of these. So intuition, I'm not. ChatGPT. What's the use of it if I will not use it right now? Okay, I will use voice mode. Think. Upgrade to plus. Discuss the algorithm. Okay. Maybe I'll give the editorial option here. Hey GPT, actually I'm just trying to understand the Discastra algorithm, but having problem to understand it because I'm not getting the intuition behind using the priority queue. So could you please explain it in a proper way so that I can get the intuition, because I'm not unable to uh, get the intuition for choosing the uh, queue priority queue over queue, because I took one example and when I solved it using both approaches, it is giving the same result. So I'm not sure which part am I missing. So I'm sharing you the link. Just to give me. Okay. Okay. Just give me. I just am. Yes, the exact thing you are missing is not the syntax of priority queue. It is the reason discussed need to decide which node to process next. And your observation that I used normal queue and got the same answer is actually very useful clue. I will explain it from the intuition first, then we will connect it to the code from take to forward approach you linked. Forget Discastra for a moment. Think about BFS. Suppose we have A to B, weight 1, A to C, weight 5. Starting from A, 0, B, 1, distance C, 5. With BFS, we put Q, B and C, and process B first, then C. Okay. Why is that okay? Because in an unweighted graph, every edge cost costs the same. A to B, one edge, A to C, one edge. They are equally far away. FIFO works. I used to. Now introduce weight. A to B 100, A to C 1, and C to B. It wasn't able to draw graph, I think. That's why C to B again 1. There are two ways to reach B. A to B through ACB 1 plus 1 2. Now imagine we use normal queue starting from A, B and C, Q, B and C. Because B was discovered first, so we process B distance 100 before C distance 1. B was discovered. Okay, that is okay. And this is the exact problem. We just processed a node whose current distance is 100. Process nodes in order. I discovered them. Process the node that currently has the smallest distance. So instead of BC Q, we use 1C 100B. Fuck intuition. This is not the BFS asks which node did I discover first? Which node is currently closest to the source? Closest to the source. It looks fantastic. Now let's understand why your example gave the same answer. Oh, wrote the complete theory. Hey GPT, I forgot to tell you one more thing. That every time when I'm processing the node, or you from a queue, I'm looking to all its neighbors. Again, And if there, like if I'm getting lesser distance, so I'm that's why I'm maintaining a distance array, and there I'm keeping the distance that I discovered so found for a node. And if I'm founding a new distance for the node, then I'm adding it into the queue, this node and the new distance, and also updating the queue, updating the result distance for that. So in that way, suppose I processed a node with higher distance at starting, but when I'm coming from another path and I'm seeing that the distance that I wrote earlier was incorrect, so what I'll do, I will update it and I will add its neighbor, or I'm going to explore this node again. I think the problem will be reprocessing is not nonsense at all. In fact, your approach can still compute the correct shortest distance. The missing distinction is, oh, correctness versus efficiency. Suppose you do this. Zero. Oh, yeah, this one will be interesting one. While Q, no. Suppose you do this Q 0A. Okay, this is logic system. I don't care that I process a node too early. If I later discover a better distance, I will update it and process that node again. Yes, that logic works for non-negative weighted graph. So the natural question is, then why the hell do I need a priority queue? And this is where the intuition becomes much clearer. Your algorithm is basically keep correcting mistakes. Okay, A to B10. Outgoing is, so you explore them using distance 10. Later you process 1C and discovers B again. So your algorithm is saying, oops, I previously used B with 10 distance. Now I know B is actually reachable in 2. Let me redo. Make that oops redo situation less often. Situation happen much less often. After processing A instead of, so you process C first. Discover C is equals to B equals to 2, 2B, 10B. Ten B. So you reach the good distance before doing all the unnecessary work from B10. Okay, got it. And here is the key difference. I will process whatever comes next, and if I later find a better distance, I'll fix it. Before processing something, let's pick the currently cheapest thing. So ideally, we don't have to fix it later. That is the entire reason for the priority queue. Visible. A to 10. Storing the distance array because the distance I discovered earlier might be incorrect. Exactly, distance array and the priority queue have two different jobs. Okay, let me think in different way. I just got one phrase from this. It is like every time you are discovering something, uh, and from there, basically from a node. So suppose there is source node, and now you have a queue, priority queue. There are the different distances of items. These are the different distances, distance, and what exactly you are doing. So every time when you are getting, you are starting processing the cheapest node, or you can say shortest node first, and then what exactly you are doing. From there, you are exploring all the paths. Okay, and then what exactly you are doing? Basically, you are adding them into queue, and now again, what happens exactly? You are again selecting the cheapest one, selecting cheaper one, and reason behind it is simple, because you are already calculating the cheaper distance, or shortest distance first. You are giving more priority to those nodes that are calculating the lesser distance. That means what will happen? Suppose there is a you already calculated something smaller. If you are getting from a node to reach a particular node, because those nodes were smaller, now when you will move from another end, that is already bigger number, then you don't need, you won't process it again when it will come in from, when you will pop this item from the queue. Okay, little I got little intuition, but I don't know how long I will remember it. Okay, what's the time right now? 1 hour 26 minutes. God help me. So this is okay now. I will just check the fact question. Where is it? Um, yeah, it's a now. Let me just think about the question that were there were some frequently asked questions occurring out. Node once it assumes that once a node is processed, its shortest distance is finalized. After process, but it will work for negative weights. But the thing will be, what will be? Suppose from here you got something that is negative. So what you did simply, from you choose the minimum one, minimum distance to reach to these sources, and from there you will move to another node. Always picks next closest, ensuring that we process the shortest known path first, improving efficiency. How would you modify this to return to actual shortest path, not just the distance? The graph had negative weight edges. Oh bro, there are so many. Will it handle negative? Once the smaller distance node is removed from the priority queue, its distance is final. Really? Add process B before C. Bro is asking college. Bro, I'm not in college. I've completed my college, bro. Okay. So here, let me share the code and I'll ask it. Seems like maybe I have implemented it in a wrong way. But but in this approach, I am checking all the neighbors again. Then will it not update result? Trace your exact code. Distance 0. Initially 0, 10, 1. Out first. We process C. New distance 1 plus. I will check the code. Yes, bro, I'm working somewhere in a stupid company. I won't tell. Just don't ask me company and anything related to company. That's why I'm learning. Okay. Okay, so what's the tutorial is written? They have kept the same thing. Mm-hmm. Because some confusion is here. Then why do many implementations have this fancy? It says the heap gave me an old version of this node, better distance, so don't explore its neighbors again. If distance itself is bigger than the give me an old version of this node. Will it edges? How will it not work? Start at A, your heap initially gets 0A. Process A, distance B. I will do it myself. Why would I? So you have node A to B and A to C. A to C and C to B. So 2, 5, A to C and minus 10. So at the starting, Q will be something like, where is it? It will be having two things. First, distance, let me keep everything 0 for, let's say this is a starting node, source. So 0, I will say A. 0 is A, 0, 1, 2. So 1, 2. So to infinity, infinity. Now what I'll do, simply I will start from 0. So 0, distance is 0. For node 0, the distance is 0. And from 0, you can go to C and D. So what you will do, simply you will pop and you will say C. You are going to go, so for C, so basically 1, node 1 and distance is 5. So 5 and 1. You will add, and second 2, and for it the distance is 2 comma node 2. So you added 2. Now it will, based on min heap, it will process the first node, first 2. So okay, I forgot to add the distance. So for 1 it will be 5, for 1 it will be 5, for 2 it will be 2. This is one thing. And now what I'll do, simply I will, no, I will process this node because this is minimum one. So I will process this node. So if I'll go to 2 and I will check from here what is the distance. So B, you will say okay, B or 2 you can say. So from 2 you will say I can go to A, go to 0, and I can go to this. So if we are going to 0, Definitely it will be like a 2 plus 2 4, and for 0 it's 0, so you won't add. Now you will say okay, for C it is like 2 plus 10 minus 8, so minus 8, so it's better, right, compared to whatever value we have right now. So you will say if I'm going to this node, then it will be something like 2 plus this plus 8, so minus 8. So what I'll do, simply you will add C. No, 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 no. Yeah, so you will update it. What? You will update C. C means when, with the minus 8 value. So now you will say okay, I will add minus 8 and 1. And now you have two things. Now again you will process minus 8. So minus 8 you will go, and 1. From 1 you will say 5. I can go to A and I can go to B, both. So you will say okay, why don't I go to this? So 8, you will process it and you will say okay, still I have negative value, so I will be better if I will follow this route. So minus 8 plus 5 will be minus 3. So for 0 you will change to minus 3, and you will add 0 and no, not 0, minus 3 and 0. It is like I'm just looping through all the items, and from C to B you can say C to B means you are looking for B, and for B it's 2. 2 for 2 it will be something C to B. So right now what is the value of C? It is minus 8, and from here you are again moving to this. So you will say if I'll move in this way, then 8 this. So okay, minus 8 minus 10, it will change to 18. So minus 18, here it will be minus 18. Crazy, you are looping through every time, and it will be 2. That's wrong. Let me see what exactly it is saying, explaining. Process A, process A, start A at A, distance 2 and 5, distance B, distance C. So heap 2B, B and 5C. Okay. So min heap, so you pop 2B. So your code process B before C. At this point, Discustra is effectively thinking. Now suppose you have this common optimization. Do you pop 5C? New distance will be minus 5 for B. Now crazy. Discustra with a heap can never produce the right answer on graph containing negatives. So saying would be too strong. The real statement not guaranteed to work correctly with negative weights. Yeah, I can see that. negative cycle. This is where you keep updating idea becomes the real problem. A to and it keeps going on. Ah, fuck! I just observed it. Like when I was solving it using this approach, it's keep on updating everything, and it will be difficult to stop it. Oh, so lot of things are going here, and now I will jump into another. I mean, I will further explore it because I have to think. I mean, I need to think in different angles. So we solved using one submitted or not submitted.
In the previous video, we have learned about Dexter's algorithm using Gratitude.
Yeah.
If you haven't seen that video, please go back and watch it because you won't understand anything in this video because it's an extension. It's just an extension of the previous video. Okay, so in the previous video, we did implement Dexter's algorithm using the priority queue, right? But in this video, what I'll do is I'll try to implement Dexter's algorithm using the set data structure. So if you remember, what did we do in the previous video? We just took a priority queue, right? And we stored everything in terms of distance and node. Why did we take priority queue? Because we always wanted the minimum distance at first. That is the reason we took priority queue. Okay, now set. What is the definition of a set? Set stores unique values and the smallest at the top, and then it stores everything in the ascending order. If you know set data structure, it stores everything in the ascending order, right? So that is what we were doing in priority queue as well. In priority queue, we were looking for the minimum distance. If you take set, it's going to do the same. If you look at the topmost element, it will always be the minimum there because set stores everything in ascending fashion. However, there is one other reason why I am going to use this particular set data structure, and I'll explain you. I'll again doing it right on the same example. Okay, so we'll take the same set data structure, a distance, a node, a source node, and initially as usual put 0 and everything else to be infinite. That's what I'll start off with, and I'll just put off distance 0 and the source 0 in the set data structure. So let's take it out and erase it. So distance 0 with a node 0. Okay. Let's quickly move it to its adjacent nodes. I'll just go quick because you already know about it. This is going to take +4, so the updated distance will be 4. I can reach at an updated distance of 4. Thereby, I'll go and say updated distance of 4 and a node 1 in the set data structure. I can also reach the node 2 by taking a distance of 4. So another updated distance of 4. So 4 comma 2 will come here, right? And this is how we can wrap up the first node. So right after the first iteration, 4 comma 1 will appear at the top because these two are same. So it is differentiated by the node number. So 4 comma 1 will end to appear at the top. What I'll do is I'll take the 4 comma 1 this time. So the distance is 4 and the node is 1. Yes, the distance is 4 and the node is 1. So if I have node 1, where can I go? From 1 I can go to 0 and 2. So I'll try to go to 0, which is node 0, which will end up taking me 4, to make the distance 8, which I'll not consider. I'll try to go to node 2 by taking a distance of 2, which will make the distance of 6, which will not be considered. So this is done. Right, I'm going quick because you already know this. Next I'll take 4, 2. So 4, node 2. From node 2 where can you go? You can go to node 0, that will cost you 4, which will make it a distance of 8, which will not be considered. You can go to node 1 as well, which will take your distance of 2, make it 6, which will not be considered. These two things will not be considered. If you start at 2, there are other things like 3, 4, and 5 where you can go. So let's try to go to node 3. So if I try to go to 3, it will take me a distance of 3, which will make me a distance of 7. That will be considered. So 7, 3 will be considered. So you can put that into the set data structure, right? You can. So once 3 is done, we will go to the next node, which is node 4. And how much will we take? We'll take 1, which will make the distance as 5. So 5 comma 4 is now the shortest one. It will go at the top. I'll update the distance here, which is the next node. The next node is 5. I'll take a distance of 6, which will make it a 10. So 10 comma 5 is what goes into the set, and we'll update 10 over here. So I can tell this iteration is over. So we can just go and omit this portion of, okay, done. Now, is where you understand. Let's go to the set and get the smallest one, which is 5 comma 4. Distance of 5, which is the node 4. Okay, where can 4 go? 4 can go to 2 if you carefully see in the graph, which will take it a distance of 1, which will make it at 6, which is not to be considered. But from 4, you can go to 5, which is going to take 3. Plus 3 is what it will take to go to 5, which will make it 8. And this is why you see, previously, 5 was reachable at 10, not infinite. If it would have been infinite, please hear my words properly. If it would have been infinite, it means no one reached it ever. But since it is 10, it means someone reached 10. Someone reached 10 previously. Please hear me out properly. At 5, we do not have it infinite, we have a 10. Had it been infinity, it means the first time someone is reaching 5. But since it is 10, it means someone has reached 5, which took him a distance of 10. So I'm sure there will be a 10 comma 5 in the set. I'm sure there will be a 10 comma 5 in the set because someone reached 5 at a distance of 10. I'm sure, right? So if I'm sure, I'm getting a better one and I'm putting that into the set data structure. Something like an 8 comma 5 will go here. Like if I go and erase this portion, something like an 8 comma 5 will go here. If an 8 comma 5 goes, is there a point in keeping 10 comma 5? No. This is where you see, I know the set will have a 10 comma 5. Set, please erase it. Priority queue cannot erase. Priority queue will do the iteration. But set will say, I have a liberty. I can do this erase operation. I'll go and erase it. The moment I see there's a better alternative, I'll definitely put in 8 comma 5. But before putting it, I'll say, there's no need of 10 comma 5. I can reach 5 in a much better distance. And if I can reach 5 in a much better distance, why don't I use that better distance? Why will I end up using 10? I don't need extra iterations. I don't want in the future that this happens like this. I don't want in the future that in the next step probably I'll get 8 and I'll do for 5, and then again I'll take 5 and do it 10. That won't be of any use because if 8 was taken prior to 10, it would have given me the shortest distance. There's no point in taking 10. This is why I'll use set. I'll use set to erase. Very important. I'll use to erase
How
already
we will
existing parts.
implement such a
Already
set?
existing parts. Does it improve the time complexity? Very, very minor.
Because we are
Not
relying on
much.
the
Very,
second
very
node
little.
and the
Depends on the
value that
class,
is
but
maximum.
it's better that you use set because even set will go as even if you do an erase, set dot erase is a logarithmic operation. So can I see that if I use set, it will be better complexity than predicate? No, right? Because set dot erase ends up taking a logarithmic time. So you are probably saving up on iterations in the future, which might not be, but you're erasing it. So
Oh,
erase takes login.
we need
So
to
you're investing
erase
a login,
and then we
and in the
need
future
to
you're saving
insert.
some iteration. So depending on the size of the graph, a lot of things will different. So you cannot explicitly tell me that set is better than predicate or predicate is better than set. Both of them can be used because it'll be hardly a minor difference. This is how you tell to the interviewer that these are the cases where I can use, these are the cases where I cannot use. If you tell the interviewer with such concept clarity that you know like almost every bits and pieces, you will be impressed and tell you learn from Kiki forward. Cool. I hope you understood the algorithmic implementation. Now it's time to code it up. We'll be coding the C++ on the right, and
I will do lot of I will do little practice on terminal Python 3. Okay, L is let's say we have a set of crazy. S is set and S dot add tuple 1 and 2. Let's say 3 and 1. S dot add 3 and 2. So definitely these are the different S 3 1 3 2. Add 3 comma 4. Sorry. Okay, so the length is 3 1 2. Crazy. What you did, bro? Okay, let's do one thing. So distance is 3 for 1, 3 for 2, and let's say 4 for 1, and is dot add 5 for 1. So there S print. So far the node 1 distance are 3 3 no 3 4 5. So S dot remove, I think remove is the 3. S1 set S1 dot add 1, S1 dot add 2, S1 dot remove 1. Suki, I need to set. An item use remove, raise keyer if missing, discard, fail silently if missing. If I have a set of tuple and I want to remove all items having the same second value of tuple. Okay, okay, let's do one thing. First, let's see S. So you can see three values, 4 then 5 it kept, and let me add S dot add, and I will keep like a 0. 0 is the distance and value is uh, okay, 3 1 3 2 4 1 5 1, 0 comma 1, 0 1 first will it will come, then 3 1, then 5 1, then the 3 2. Yeah, it's weird, right? Logically it should be 0 1 first, then the first value 3 1 should come, 3 2 should come, then 5 should come. But this is not that way. Are you crazy? If I have to sort, then it will be list only. Then what's the point of using set? Something, some there are some.
That's a tough
I will see the solution. It's like I'm spending a lot of time on disgust. Min heap for set also. Seems like this option is not okay. They kept the same solution here as well. Bro, is this limitation of Python? In C++, I remember there was an option will sort, and there is unordered maps and all. Let's forget about that first. Let's jump to time complexity. Oh,
In the previous couple of videos, we have learned about Dijkstra's algorithm, if you remember, and we solved it using a priority queue and a set data structure. And there were a bunch of questions revolving around your head. Why priority queue? Because even if we take a queue data structure, it does work. The time complexity I stated was E log V. Why E log V? A proper derivation of that. What is the intuition behind Dijkstra's algorithm? That was another question that would have come to your head. So I'll discuss all of these 3 points in this particular video. So coming across to the first question, why a priority queue or a set? Because even if we take a queue data structure, we do get the answer. So let's take this particular graph, and this will be the corresponding adjacency list. So let's try this algorithm with a queue data structure and a distance array. Okay, so we give it the source 0. So apart
oh,
from
we
0,
already
everything we can
explained.
initialize as infinity, right? So source is put as 0, and we'll put 0,
I'll
comma
be
0 in the queue data
I'll
structure.
be
Let's take 0, comma
available
0.
in 2
So
minutes. Just want to go to washroom. So where is my break? Go. Okay, let's begin again. So where is my screen? I hope you can see me. Mastering Q data structure implemented. Coding wala. I don't know what people are doing. They are doing great. Two pointer algo pattern question on lead code. Oh god. Two pointer algo pattern question on lead code. Oh god. Is it me the one who was watching? Two pointer algo pattern question on lead code. I'm getting pressure, bro, when I'm seeing people making rocking. It's not going to work.
0 at a node 0. Where can node 0 go? Node 0 can go to node 1 and node 2. Remember, first node 1, then node 2. First node 1, then node 2. So if you try to go to node 1, the distance taken will be 3 and the updated distance will be 3. So I can update this with 3 and I can say 3 comma node 1, right? And if I try to go here, it'll take a distance 1 and the distance will be 1. So this will be 1. I'll be like 1 comma 2 is what I'll put into the queue. Now remember, it's not a priority queue, it's a queue data structure. So we get the next element with a distance of 3 and a node of 1. Where can 1 go? 1 can go to node 0 by taking a distance of 3, which will make it a distance of 6, not to be considered. 1 can also go to node 3, and that will take a distance of 4, which makes it a total distance of 7. Update 7 and put 7, 3 in the queue. So this is also done. Now let's take the next element. The next element comes out to be 1 node equal to 2. Where can 2 go? 2 can go to node 0 with another 1, which makes it a distance of 2, not to be considered. 2 can also go to node 3 with a distance of 2, which makes it a total distance of 3. So node 3 is having a better version 3. So 3, 3. Perfect. Next. So point of observation. Observation 1. Whenever you add 3 now, you came by one path, which took you something like 3 plus 4, 7. So 7, 3 is there. And you came by other path, 1 plus 2, which is 3. So 3 is also there. So there are two paths which are there. Now, if you would have used priority queue, you would have actually dealt with just 3, like this path, instead of dealing with this path. And since you're dealing with a queue, you end up dealing with 7, 3, which is a bit of time consuming. Okay. And now 3 can go to 1, which will take it 4 and makes it a total distance of 11. 3 can go to 2 as well, which will take it a distance of 2, which will make it 9. Both of them will not be considered. And then it can go to 4, which will take a distance of 2, which will make it a distance of 9. So 9, 4. It can also go to 5, which will take him a distance of 1. So the total distance will be 8. 5 will be 8. So 8, 5. Perfect. So done. Next, we'll just omit everything. And next, we'll come up with the next guy, 3, 3. So again, we have node 3. Now, 0 will not be there, 2 will not be there, because these things are not possible. Like you can't go back to there because the distance will be more. But when I try to go to 4 this time, it takes a 2, which makes it a better distance of 5. So 4 got a better distance of 5, 4, right? And you can also go to 5, which will be plus 1, which makes it a distance of 4. So 5 can also be done with 4 distance. So this is done. Did you see something? Unnecessary occurrence. Did you see something? I can reach 5 using 4, but there's still an occurrence of 8, 5. I can reach 4 with 5, but then there's still an occurrence of 9, 4. Why did that happen? Because you also considered this path. You also considered this path. Then you came and considered this and this. Had you used a priority queue instead of this, then this 7, 3 would not have been considered. This 7, 3 would not have been considered, and you would have considered just 3, 3 at the first. So afterwards, when 7, 3 would have arrived, it would have not found shorter distances. That's why using the minimal distance is preferred, so that you don't encounter a lot of paths. So you're just doing a brute force if you use queue data structure. You're going on all paths, and then figuring out the minimal. And I'm like, I'll go, but I'll be like greedy. I'll go to the minimal first, so that I can mark all the minimal that I can reach. Then I'll go to the other guys. That's why a minimal is important. Otherwise, you end up exploring too many paths. It will give you the answer. I'm not saying that it won't. It did give you over here, but you're exploring too many paths. Unnecessary occurrence of these guys. Unnecessary exploration of paths. Unnecessary iterations. So I hope I was able to explain you why a queue is not preferred, because it takes a lot more time complexity. I hope the intuition is also clear now. Because of priority queue, we always travel to the minimal guys first, and we explore minimal, and we ultimately have reached all minimals. Since you're doing a traversal thing, we reach minimals always. Cool. What's the next thing? The time complexity. Why the time complexity is E log V, where E is total number of edges, very, very important, total number of edges, and V is the number of nodes. Why is that? So, is this the pseudocode of priority queue? It is. This is how the pseudocode of the priority queue looks like. So I'm saying while PQ dot not empty. So At max, I can say that this loop will go through all the nodes, which is V. At max, like twice or thrice. It won't go like a lot of times because if following greedy strategy of going to every node, every minimal node. So I can say this while loop is going to run for the total number of nodes, which is V. So I can say this probably will run for V, right? So V into the entire thing. V into this entire thing, correct? So V into what? This is going to take a logarithmic of heap size. Heap size is very important. Logarithmic of heap size at the worst case. This is number of edges. This is number of edges of every node. Number of edges of every node. Let's take the densest, like the most dense graph, where if there are 4 nodes, for an example, this is one node, this is connected to everyone. And this guy is also connected to this, and this. This guy is also connected to this, and this. This guy is also connected to everyone. This is the most dense node, where everyone is having n minus 1 nodes. Every guy is connected to all other nodes possible. That is the most dense graph possible if you avoid self loops. I don't want self loops. I want this guy connected to everyone. I want this guy connected to everyone. I want this guy connected to everyone. Got it? I want this guy connected to everyone. That is what you call as a dense graph. So I'm taking dense graph and I'm saying any. Any is what this will iterate at the worst case. What can be any if I ask you? If every guy is connected to all the nodes, how many nodes can one have? So can I say it'll be V minus 1? Because if you see, this guy is connected to 3 in 4 nodes. One he himself, other 3. So V minus 1. So you can say this will run for at max V minus 1. And then there is an a conditional check, which is okay. And then there is another push, which will go for log of heap size. Understood? Perfect. Till now. So if I write it properly, can I write it something like this? V in overall into pop vertex from min heap, number of edges on each vertex into push into the priority queue, isn't it? This and then any into push, correct? So if I go across, I need to write it. Can I write this as V into pop log of heap size plus any into log of heap size? I can. I'll go. And can I say any is nothing? Like, can I just take logarithmic of heap size to be common? I can. If I take logarithmic of heap size to be common, I'll have any plus 1. Yes. Okay. Next. I figured out what was any. Any was V minus E, because at max, everyone can have V minus 1 adjacent nodes at max. So can I replace this with something like V minus 1? So minus 1 and plus 1 will go. So will it be like V into E into logarithmic of heap size? It will be, which is nothing but V square into logarithmic of heap size. Indeed. Now, what is this heap size? We need to figure this out. What is this heap size? So when we are taking a priority queue, when we are taking something like a priority queue, is whenever we are taking something like a priority queue, at the first step, if this guy goes to this, it finds everyone to be having a smaller distance. It will indeed push 3 nodes. It will indeed push 3 nodes. This guy will end up pushing 3 nodes. Then what do? You take out this first guy. And imagine, this guy is also connected to 3 nodes again. This guy is also connected to 3 nodes again. This guy again finds better. So hypothetical, like it's a worst case scenario. It again will push 3 nodes, correct? Then you'll get this guy. This guy is again connected to 3 guys. Hypothetical again. Again it will get smaller distances and it will again push 3. So at the worst, like again you'll get this, which will again be connected to 3 guys. But you again push all of these 3. Because 3 guys, 3 separate nodes, pushing it again and again. So can you see 3 plus 3 plus 3, which is equivalent to n square nodes? Because everyone, like, it is something like n minus 1 plus n minus 1 plus n minus 1, keeps on pushing every day. Can I say somewhere near about V square nodes is the worst heap size? Again, very hypothetical scenario, will not happen. I'm taking the extremist case. So can I say the heap size is nothing but V square? I can. At the worst case, everyone is pushing everyone into the heap size. Okay, cool. Now, what is logarithmic of V square? Can I write it as 2 log V? I can. Right? Now, what is V square is my question. That's the total number of nodes. So can I convert this into E? You might again ask, how? Do it as simple. If one guy is connected to 3, and everyone is connected to 3, that is, like one guy is connected to n minus 1 nodes or V minus 1 nodes, right? And there are V nodes. Everyone is having V minus 1 edges. How many in total they will have? V square edges, which is the total number of edges, correct? If one guy is having V minus 1, there are V nodes. V minus 1 into E is V square, which is the total number of nodes. I can simply convert V square into E and be like E into 2 log V, which can be written as E log V, which is the time complexity worst case, very hypothetical, worst case scenario of Dijkstra's algorithm.
This one looks complex, or it's already this is a complex topic, I feel. So I will add a note. Must revisit and try to deep dive into it. Okay, so 1 minute, bro. Yeah, I haven't lose. Okay, to go short, discuss. No, this is another option. Discuss. So this one, Discastra, market done. Very important. Why priority queue is used in Discastra algorithm? Is it a salute question? They kept the same question, just seems like dynamic option they have used something and uh, shortest distance in a binary maze. Let's solve it. Hard. Every problem is hard only. Given an n cross m matrix grid, n. Okay, they are using n cross m. N cross m. N. Given an n cross m matrix grid where each cell contains either 0 or 1. Determ- de- Determine the shortest distance between a source cell and the destination cell. To adjacent cell up, down, left, right if the adjacent cell has a value of 1. When this one can be solved with multiple approaches, I believe. If the destination cell is not reachable from source cell, return -1. I mean, determine the shortest distance. Chat disconnected. Successfully connected. Okay, connected, bro. Okay, so given matrix n cross m, let's take example grid 1 1 1. Four size grid, and there are how many rows? 1 2 3 4 5. So 1 1 1 1 1 0 1 1 1 0 1, and third one is 4 times 1 1 1 1, and fifth one is 1 1 0 0 1 1 0 0, and fourth 1 0 0 1. Okay, source 0 1. So I will do one thing. 0 1 2 3 0 1 2 3 4. So source is this 0. Wait a minute. Source shortest distance between a source cell and the destination cell. You can move to an adjacent cell up, down, left, right, created out of cell containing 1. Source is 0, comma 1, and destination is 2, comma 2. These are the known. Where is that? My note. Yeah, it's a. So let's do one thing. I will start from here. I will go to here. If I have to use dynamic programming, can we solve it using DP? Because I already learned the DP. I solved the problem on DP. What you will do? problem with DP will be like here you are not moving in one direction. Uh, it should construct or it should minimize the problem, but here you are moving up, down, left, right. You can move up, down. So the problem will be, imagine suppose you are here and you are trying to reach this location, so you will move here, correct? So you can go to here. I'll copy it. Let's see why we can't solve it using the cannot be. I will keep it somewhere. Go bro, go bro, go. Mosquito, where are they? So here too you can move. Suppose you are here, not here. I will say like, imagine, imagine. You are here. Now you decided to move to this location. So you can move, and you have other options. You can move here, you can move here, and you will check what is the distance from this, and this. Okay. Now you will ask these nodes to explore. So it will explore. Is it possible? No. It will say check this. Suppose we are checking from this. It will try this option, and it will try, is there any another option? It will move to it again. So every time you are trying all possible option, right? Okay, then that means sometimes you will get same options. I mean the same problem again and again. Like suppose you are here. From here you can go here, and you will reach here again. But you will say, okay, what is the minimum value from here to it will loop through all the time. Instead of reaching to a conclusion. Now let me think in the graph point of view what exactly we need to do. So you will be having source, you want to move to a path. So if I have to build adjacency list, 0 comma 0 to its all neighbors. You can say, so its all neighbors will be these different nodes. So basically I think I don't need adjacency list, because here you can get whether the node is existing between this node and all. So okay, let's assume. So these are the different nodes, and we wanted to reach to this node. And whenever we are moving from a node to its neighbors, correct. For example, for 0, 1, its neighbors are 0, 0, and 0, 2, and another one is 1, comma 1. Okay, so these are the neighbors of it. Now you will check. So for 0 and 0, it will be distance will be 0, and you are moving to these nodes. So the definitely distance will be 1 only. Whenever you are moving to its neighbors, the distance to reach to that node will be 1 unit here. Correct. Now, what exactly we will need to do? So we can move using the BFS. I guess we can solve it. And you will explore all the options that are from here to here. I mean, not here, but you will see if you are able to reach to that node or not. But all the nodes have the same distance, so why if I will explore all the paths? No, no, no. You're getting into the wrong direction. Is it showing my channel only? Like, am I watching or what? Just wanted to see. Is it showing my channel? Oh fuck! I have kept the audio very. Like, am I watching or? Yeah, I'm only the one. Wanted to see. No, it's two. Is it? Is it showing my channel? I think because of here something is wrong. Oh, one thing let's forget about that. I so suppose imagine I have this question, different nodes. So here you have different ages, different paths to reach to this location, and you want to minimize, get shortest. Imagine just I will push everything into the queue. So 0 to, let's do. Let's do just a dry run first to get it, or just can I visualize it? So imagine here you are at 0 and 1. So what you will do, you will create a queue and we will push 0. This is node, and what is the distance for it? 0 and 0 comma 1. This is one thing. And now you will do, you will check all of its neighbors. So you will push one distance for 0 comma 0 and another for one distance for 2 comma 3. I did 0 comma 2 and one distance for its another neighbor, that is 1 comma 1. Now if I will use priority queue, all have length same. One more thing I will check first. Imagine what exactly is happening. No, not here. This is, will it be source will be okay. They just kept source and destination, but it would be source is here and destination is here. Now minip what it will do, it will choose any one of them, then there will be problem. If it will choose this one, then again it will explore all of its neighbors. Let's say it took 1 comma 1. Let's see, it took one, let's say it took 1 comma 1, this one as the priority. So 1 comma 1, then that means where is 1 comma 1? 0 comma 1, 1 comma 1, no. So let's say it took 0 comma 0. I just want to worst case 0 comma 0, it took this one. So 0 comma 0 distance is 1. So what it will do, it will choose this one 0 comma 0, and what is the distance for it? 1 comma 0 and 1 comma 1, and no 1 comma 0 and 0 comma 1. So for 0 comma 1 you are already getting 0, so you won't touch it, you won't change, basically update the value. And 1 comma 0, so you will say 2 and 1 comma 0. Now you will choose again these nodes and you will get into this and this one. So again, so this is done, all of its neighbors, and now you will move to this one. Okay, let's say 102 102 102 this one. So here you are, and for this its neighbors are this one. So you will say 2 distance and the node is 0 3, 2 distance 0 comma 3, one node, and another one is not possible. This one you will say okay, it's not going to get proper result, I mean it's a higher value. Now you'll move to this 1 comma 1 comma 1, I mean one value, weight value distance is 1, and for 1 comma 1 this cell. So from here you can go there, you can go to here, you can go here, no, not here, here. So for 1 comma 1, 1 comma 0 you are again visiting, and for 1 comma 0 you will say what is the value? Okay, 1 minute. For 1 comma 0 you are getting 2, 1 comma 0, and 2 you already updated, so you are not getting better value. So you will say okay, no problem, I won't go to this node. So you will simply go to this node, I mean this one you won't explore, this one is not possible, this one here you will get 2 comma 1. So 2 comma 1 and distance is 1 plus 1, 2, 2 and 2 comma 1. So okay, it's good. So this is done, this is done. Now here you will choose, all of them are with the same distance. So 2 comma 2 comma 1. Again, every time you are checking whether you got this one or not. So let's say 210, 2 distance 1 and 0. So here you will say from here you are going to this node 2 comma 0 and 2 this one. So for this you already got the minimum distance, so you want to update, so only you have options 2 comma 0 and distance will be 3 3 2 comma 0. Okay, now again then you will take minimum, so these two, so this is done. 203 20 2 and oh 2 is distance, 0 and 3 0 3. So you will move here 0 3 2 distance, so for you from here you can go here and here, so here you are getting minimum already, so here you will move 0 3, and for 0 3 you will move to 1 3, so distance 1 3 and 1 3. Okay, perfect. So this is done. 203, this is done. 203. Okay, now 2 1 2 2 1 2 2 1. So this way you will get the result, but is it optimized? Every time taking minimum. That is okay. Here you don't even need priority queue. You can do it without priority queue, because if you notice one thing, every time you are finishing all the same length node first, then you are moving to another level layer, then you are moving to another level 3. So that is why even priority queue is not needed. You can solve it using simple uh, queue. But the only doubt I have, even after getting value, okay, yes, one thing that I got. Once you got the result, oh, I'm not sharing my screen. When it happened? No. So here to here, every time you are storing the data, you are checking whether you found the target or not. Target or not. If you got target somewhere, that means you, if you will explore other paths, definitely it will be higher value, right? Compared to this one. Correct. Higher value. Also, if you have visited a node, no, 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 that won't work. I have to keep the distance value. Based on that, I need to post the item. Suppose, let's say, what happens? I have one solution. Q. I can use Q for it, but I'm just concerned about optimization, whether it will be optimized or not. Whether will it be optimized or not. For example, just wanted to cross check when we are getting from one level to another level, and if you are getting source, if you are getting target somewhere, that means if you will explore further, you are going to get bigger number for sure. One thing. Second thing, do I need to keep the distance array or not? Can I blindly go to this and check whether target found or not? That I wanted to make sure. So basically, you from shows node, you exploring all the paths that are possible. Yes, correct. Then you are moving to next level. If something has already been taken care by other in the previous, someone already reached uh, earlier, that means that their level is smaller compared to this. Distance is shorter because we are processing level by level here. That is happening because one has equal distance. So if I will keep the distance matrix, then I won't get uh, into the same exploration again. Correct. So let's do two things. Distance. How to maintain distance? How to maintain distance? I need to take a half size. Everything will be uh, okay. Grid. So grid size will be m is nothing but len of grid. N is nothing but len of grid of 0. So in range m. Python terminal, I need to learn basic Python. I believe I've forgotten. So here we have a distance array. We kept everything as source. What will be the source? Source. Okay. So distance. Let's initialize it. Distance of source. I will do distance of source of 0, 0, comma source of 1 will be 0. Okay. We'll start from here and we'll move further. So okay, let's do one thing. X is nothing but source of 0, y is nothing but source of 1. So let's make it easy. Y is equals to 0. This is 1. Let's use q. Come on, bro. Brother, come on. From collections import q. Deck. Double-ended q. DQUE. No. DQ deck. This is the q. While now you need to push the first value and keep the distance. Okay, keep the distance. TQ dot push append. I remember append two things. First value will be the distance, that will be 0. Second value will be, I will keep in single tuple, so 0 and x comma y. So take it append while not dq, while q dq, post pop the item neighbors nbrs is equals to, here you can say 0 distance. Okay, up down left right. So up means you are changing 1 to 1, down 0 minus 1 xy, and here left minus 1 0 and right 0 1. What the heck you did, bro? 0. I will copy, keep it moves is better. Okay, dq dq. So node, no, x y, or let's say I and j, xy. I will keep xy and d for dist, and d is equals to, no, you can keep anything d xy, otherwise will be there dq pop left. So I'm just popping the item from the queue, and every time when I'm popping the item, okay, so distance we have right now this, and then what I'll do, every time I will get the, if, so you already added this distance, so you don't need to take care of that. Okay, now what I'll do, simply for move in moves, you will check, so move, so you will say I will be x plus move of 0, and j will be x plus move of 1. So you got this. If I less than, greater than equals to 0, and I less than m, and j greater than equals to 0 and j less than n, that means it's a valid move. Okay, you can say it's a valid move. If, think one more thing, that is d plus what, 1 is lesser than the distance of I and j. If I and j, if we are taking move and its distance is lesser than this one, then only you will do one thing, you will post dq dot append append what, you will append three things, so d plus 1, and another thing is I and j. Also don't forget to add distance 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 of I and j. I think I need to do it faster, bro. I feel like I'm working in sloth mode. So this is one thing. Okay, only then you are adding the distance, otherwise you are not doing anything. And something is already visited or distances, then you don't need to take care of visited. You don't need to make visited array for sure. And okay, so this is one thing that you are that we are taking care. I'm taking care. Algorithm is taking care. Okay, at the end, so you will get the shortest distance. Okay, 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 one thing, don't forget. So this is one thing. Okay, so one more thing I wanted to do, a flag I will keep here. Flag is equals to false. So whenever you got some, suppose imagine you got distance, then you don't need to move to further levels, right? Correct. So if you can say I equals to destination of 0 and j equals to destination of 1, then break, but before break, flag equals to true and break. If flag, if not flag, break, and at the end you will get a return distance of, okay, destination. I don't want to do this, to be honest. So trg tx equals to destination of 0 and ty is equals to destination of 1. So I will end up here tx ty. Something is wrong here. I don't know, indentation is not working properly or what. Yeah, very good. Flag false. I'm just taking care of the wrong input, but it is not going to help me still. Something is wrong in the question. But I'm worried about my performance. I feel bad about me. I'm doing getting -1. Crazy. Move 0 x in x direction 0, y1 0 1, and 0 -1 -1 0 1 0, while dq x y d distance you got, flag false for move in moves I equals to x that you got from here. If d plus 1, the distance that we are calculating right now. One more thing I forgot. But still, if d plus 1, distance plus 1 is less than equals to distance of ij. xy. move, I will say I and j and t plus 1. So 1 distance 0 1. 1 1 0. Move distance 1 1 0. Fuck, what weird. I just feeling somewhere I'm making mistake, and because of that everything is fucked up. 312. God, same approach, same mindset. Time, how much time? Oh god, 3 hours. 0, 1, 2, 1, 1, 0. 0, 1, 2, 1, 1, 0. How will it be possible? 0, 1 can move. Something is wrong in the move itself, seems like. One zero. X value 1. Y value should be 1. Oh shit. Bancho, क्या किया? One silly mistake. Oh man. Tutorial I will watch first. See if my approach is incorrect. I see one thing. What is wrong with it?
So in this video, we're going to solve shortest distance in a binary maze. Now you're given an n cross n matrix where each element can either be 0 or a 1. You need to find the shortest distance between a given source to a destination source. Destination cell. The path cell to the other cell, the distance taken will be 1. That means we are moving from one cell to the other cell, the distance taken will always be 1. So now you must be thinking, if we have to figure out the shortest path, which kind of movements are allowed? So over here, you can only move in 4 directions. It is not mentioned in the question. I'll ask the problem setter to edit it and add it up. So you can move in 4 directions. So assume you're standing here, you can move here, which will take one move, then you can move down, then you can move down, then you can move here, which means it is going to take you 5 steps. Yes, because a cell to another cell takes 1 step. You can also move in this direction, in shortest distance. If it was 8 directions, you could have directly moved here, and directions will be like here from source to destination. Now, if the question would have allowed you 8 directions, then you'd have gone like this and then this. So it would have been 2 steps. But and this, which will end up taking it as well. But we are over here to figure out the shortest path from a given source to a destination. So whenever there is a question of shortest path, you always start thinking of which algorithms do you know about shortest path. And one of the algorithms that you know is of the Dijkstra's algorithm that we have learned in the previous video. So if you haven't seen the previous video, go back and watch it. Priority queue and the set data structure. Okay, now we will be solving this using the Dijkstra's algorithm as of now. And then I'll be telling you, should we use a priority queue or can a queue suffice or not? I will be telling you all about that in this particular video. So make sure you watch the video till the end so that your concept is clear enough. So if you remember the Dijkstra's algorithm, what did it state? It always stated that you need to take a priority queue. Remember? So what I'll do is I'll take a priority queue and a distance array. So over here we have a 2D array of patient will contain our priorities. So let's create the initial, which is going to store the distance at the first and then the coordinates of the node, which is over here the row, and the on the source will be 0 at source, which you can put that with each. Oh, is to the, because it's not a valid cell, I can tell it is it 0 another. So thereby what I can keep before, and I got a better version which is 1. To take 1 comma to the bottom. So if you just add a plus 1, the bottom one is 1 comma 1 is what so end up taking a distance cell. So and I'll update it. Now, here comes a point of observation. You started with a cell 0. You started with a cell 0. And then you took plus 1, plus 1, plus 1 on all the corresponding adjacent nodes. So you reached everyone with a distance of 1. Why did we use priority queue in Dijkstra? I've already made a video on that. Please go back and watch it. The reason we
Shortest.
used priority queue in Dijkstra was because we wanted the minimal of them. We wanted the minimal of them. But if you carefully observe, everyone is having the same distance. So do we need a priority queue? No. Why? Because even if you take this guy for the next step, so that means it will have a distance of 1, and again it will travel to its adjacent, again it will travel to its adjacent, again to its adjacent, again to its adjacent, and everyone will be at a distance of 2. Everyone will be at a distance of 2, and they will pile up something like this in the priority queue. And the next step, there will be 3, 3, 3, 3. So, do you need a priority? What was the purpose of priority queue in Dijkstra? It was to figure out the minimal of all of them. But if you store them in a queue data structure, they're already stored in the increasing fashion. They're already stored in the increasing fashion if you carefully see. First 1, 1, 1, then 2, 2, 2, then 3, 3, 3, then 4, 4, 4 will be stored. Why does this happen? Because everyone is increasing by a unit distance, a constant distance. In Dijkstra, what was happening? If there was a node, it was going to other node by taking plus 4, sometimes plus 10, sometimes plus 15, sometimes plus 2. It is moving. It is taking different h weights. Thereby, we did not know what was the distance. Hereby, we required the priority queue. Figure out the minimal. Do we require a priority queue over here? The answer to that is we'll still store everything in the increasing order. Thereby, we will omit. We do not need the additional logarithmic of n, which is in question here. We have proved that this problem can be solved using Dijkstra's minimal distance because added n 0, 2, go and go to the 2, and then put it into the queue. Can it go down? The answer to that is no. Why? Because it contains something as 0, which is not allowed. Can it go left? Yes. Let's try it. It tries to go to the left. It is 0, 1, which is to the left. It will not come up with it. So happily this is done. Next, in the next element, which is takes a distance of 1 at the cell 1, 1. Where is 1, 1? Let's figure out. Here is 1, 1. Can it go to the top? 0, 1, 0. So it tries to go to the top. See, updates it because it's on the left. It has 0 with a distance of 2. Pattern 0 increase. It comes to the 0 go to the left. Not to be considered. Can go down with 152. We have already reached it using a distance of 2. So we do not consider it. Because if you come by this, or if you come by this, it's pretty much the same. So we do not consider anyone and we will just erase it. Yes, we will just erase it. Next comes 0, 3. So I'm taking a distance of 2 to reach 0, 3. Where is 0, 3? Here. Can it go top? No. Can it go right? No. Can it go down? Yes. It can go down. 3. Can it go left? It can. Try to opposite is next I'll get the next guy, which is distance of 2, and the cell was 2, 1. Where is 2, 1? Let's see. 2, 1 is here. Can it go to the top of 3? I'd go to the. If this is equivalent to the destination that you are looking for. This is equivalent to the destination you're looking for. So what it does is, it says, wait, stop it right now. Stop the algorithm right now and return distance 3, which is my answer. Which is my answer. This is how easily you can solve it. That's one. That's
Correct.
If you travel by 4, rho minus 1.
So approach is same. Perfect. Okay, let's do one thing now. Again, I stop it this time because the question is, but I took a lot of time to solve it. So that's all in this video. And if anyone is gonna watch, thank you so much. Bye bye. Take care. And right now nowadays I have started using the front camera because I'm getting lazy. I don't want to turn on my phone and keep it in the side view because even front camera is not bad. So, okay, acceptable. Here we are not for the for showcase. Sorry. Bye bye. Take care and good morning. Good morning, guys.